Okay, so the modes are, we already said that there is a constant current mode and there is a constant temperature mode. So in the constant current anemometer, which is also called the CCA anemometer, the current is through the sensor is kept constant, which we already said. Okay. The advantages are that it can give you very high frequency response, but the disadvantages are these are difficult to use. The output decreases with velocity and there is a risk of probe burnt out. Okay, so in the case of a current constant current anemometer, so the current is kept constant, but what is happening is that it can actually lead to burnt out of the probes. Remember, because the temperature is the one that you are kind of measuring in this particular case. Okay, because the temperature changes. Okay. The other one is a constant temperature thermometer or the anemometer or the CTA. So again, you see that this is one part of the one leg of the circuit. So the sensor resistance is kept constant by the servo amplifier because advantages is very easy to use. It has got high frequency expense, low noise. It is accepted standard also, but it has got a little bit of a complex circuitry. That means the electronics is a little bit complex. So, but essentially it is a balance of the Wheatstone bridge that actually enables you to measure in a constant current or a constant temperature anemometer to measure the fluid velocity. So this is, for example, a pretty complicated 3-wire or 3-direction anemometer, and there is a 3-channel with triaxial wire probe. So this is very complicated. As you can see, there are wires crossing it all over. So this is a pretty hard configuration, and this requires a lot of calibration and very difficult to use also, not very easy. Okay. So in the case of a CTA or constant temperature anemometer, the wire resistance, we already know it's written like this. Forget about the nomenclature, it's more or less the same. Alpha naught is the temperature coefficient, R naught is the resistance of the wire at T naught. This is what we refer to as R ref or T ref. It's the same thing. So you can define something like a overall heat ratio as A, which is nothing but alpha naught O into TW minus T naught, and then you can actually calculate. So remember here, the wire temperature is related to the resistance, and the velocity is therefore dependent on the resistance. That's what it is, right? Okay. So the mode of operation that when the voltage is across the wire, it is like this. Okay, this is actually given by the velocity. So if or as Rw is kept constant by the servo loop, so because you are keeping the Rw constant, E square is given as A plus B Un. Now therefore E and U are basically related by this particular expression, right? So the response is non-linear. In CCA, the output decreases. In CTA, that is the constant temperature anemometer, the output increases. The sensitivity decreases with increasing value of U. So this is the kind of graph that you actually get. It's non-linear. The response is non-linear. So therefore E and U are basically you are measuring E. So therefore that gives you U. So that is what it is. Okay. So what is the dynamic response? So the dynamic response is an important part because for the analysis of the wire dynamic response, if you look at the governing equation, which now includes the term due to thermal energy storage within the wire. So this is the expression. This equation then becomes it becomes a differential equation. As we can see, you are substituting E as basically mCp(T), or in expression of TW in terms of RW. This is the combined expression that you are going to write. Forget about these symbols. You can just work out the math. It's a very very simple math. So you are basically substituting everything over here. Okay, so you are putting TW in terms of RW. So therefore you are getting this kind of a differential. So in the hot wire probe, the first order differential equation is characterized by a single time constant, which is tau. So the normalized transfer function can be expressed as this, okay, where FCP is the frequency at which the amplitude damping is about 3 decibel, which is 50% amplitude reduction with a phase lag of 45 degree. So this frequency limit can be calculated from this particular time constant, okay. So this is the dynamic response of the hot wire. So the frequency response is mainly determined by the thermal properties of the backing material. So the time constant of the thermal probe is given by this very complicated expression. Okay, it's not complicated, it's basically a large messed up expression. So where rho s is the substrate density, this is the substrate heat capacity, this is the substrate heat conductivity. So the normalized transfer function becomes what we showed earlier. So this is the one. Okay. So this is the math that you can work out in your own time, and it is kind of a little bit of an algebra, so to say. So what happens is that let's assume that you have a step change in the velocity with respect to time, because this is what you want to capture, right? And what happens to the resistance? That this kind of starts to decay. So this was the resistance. When there is a velocity jump, it decays, okay, and with time it kind of comes down to a new normal. So this decay, where it kind of drops to 63% of its total value, is what is given by this time constant tau, right? So this is how it behaves. So when the velocity changes, the resistance changes, not exactly like a step, but more as a decaying function. And over tau, it kind of quickly responds and comes to about 63% of its final value. Okay, so there will be a little bit of a phase lag, and then there will be a little bit of a time delay. So this is the time delay by which the hot wire kind of catches up with the change in flow velocity. So it can be a step change, it could be a sinusoidal change. So this is how the response function actually acts. That means how the hot wire actually responds to this sudden jump in the velocity. So the hot wire response is more characterization of the same. This is how the dynamics. So for a 5 micrometer hot wire probe in CCA mode, this time constant is about 0.005 seconds. So typically this can be improved further, but this is actually a low time. So if you invert it, that is the kind of frequency that you are going to get. Okay. So in CTA, the CTA, as we know, that keeps the wire at constant temperature. Hence the effect of the thermal inertia is greatly reduced. So the time constant is also reduced. So the time constant of the CTA is equal to the time constant of the CCA and divided by the overheat ratio, amplifier gain, and a bunch of other parameters. So this is how the dynamic, because this tau is very important. This is the time when it takes to basically adjust to step changes in the velocity. Okay, so it has got a lot to do with the circuitry, and a lot of them are proprietary information that how people actually implement this. So the typical response of a 5 mm wire probe, this is kind of given, the relative amplitudes. The phase lag is also reduced by frequency dependent gain. So these are more details which is not a part of this course, but if you take hot wire anemometry separately, you should be able to have a good idea that what this is all about. Okay. So the velocity calibration, as we see, despite there is an extensive work, the velocity calibration, there is no universal expression to describe the heat transfer from the hot wires in the film exist. So for all actual measurements, the direct calibration of the anemometer is therefore necessary. So there is no universal expression, because what we are doing is using a form for Nusselt number, which is dependent on the flow velocity raised to the power of something. So how the velocity is done, this is static calibration. So for example, you put a probe into a flow field This is, for example, a low turbulent free jet, and you are putting the probe right over there, and the velocity you can determine, and then you can calibrate the anemometer with respect to that. You can also do it in pipe flows, you can do it in other cases as well. So this is just a calibration that you require to fix that what are your constants. So this is, for example, film probes in water. This uses a free jet issuing from the bottom of a container and towing the probe at a known velocity in still liquid. So this is another way of actually calibrating it. So a typical calibration curve will look like this. This is the voltage, this is the velocity, and you curve fit U as a function of the voltage. So this is how you fit the calibration curve over a large velocity range, expected velocity range, and the corresponding voltages. And you imagine that you can extrapolate this curve, and so you can go to higher and higher velocities or lower and lower velocities, and this curve will still kind of hold, and the error is kept at a very small level. Its percentage is about like 0.1. So you calibrate it with respect to a known velocity source, where you know the velocity either analytically or using other equipments, or there is a known closed form solutions, and you use that for calibrating this probe. And you can also use low frequency in the low turbulent jets also for the same purpose as here. So the dynamic calibration is a little bit of a challenge. So the direct method is that need a flow in which there is a sinusoidal variations of known amplitude, and it is superposed on a mean velocity. So you have a mean velocity. Imagine a pipe flow which has got, say, a mean velocity of 10 meters per second, and then you have an oscillating component or a sinusoidal variation on the top of that, right? So there can be varieties of ways of actually to do this. They are all very restricted to very low frequencies as well. So you can use a vibrating probe in a laminar fluid. You can also use a microwave stimulation, and sound wave simulation of turbulence. So all these you need to impose a flow field and see how fast the anemometer actually responds. So there are indirect methods which are also called the sinus test. So subject the sensor to an electric sine wave which simulates an instantaneous change in velocity, and you analyze the amplitude response. So this is another way. So you use an electric sine wave to create the same type of velocity changes. So this is artificial that you need to do, and then you see the amplitude and see how the response is actually working. So for example, on an amplitude basis, you see up to about 10 frequency, you don't have a change in the response at all. And then this response starts to go up as you go higher in the frequency band, and then there is a sharp drop. Okay. So this is a typical wire response that you would normally associate with. So this is kind of a little on the tough side. I mean, this indirect method of sinus testing is actually you subject the sensor to an electric sine wave which simulates an instantaneous change in the velocity and analyze what is the amplitude response. Okay. So there are indirect square wave tests also. So you subject the sensor to an electric sine wave which simulates an instantaneous change in velocity, and you analyze the shape of the anemometer output, and you see that what is the response time. And for the wire probe, and the frequency limit also you can check, which is roughly about 1 by 1.3 of the time constant that you have. Okay. 1.3 times the time constant. That's what it is. Okay, so this is the kind of response that you can actually safely do. So that time constant, as I said, is very important. Okay, so as we saw, that is a function of many things, the time constant. So the dynamic calibration, the conclusion is the indirect methods are the only one applicable in practice. Sinus test is necessary if you want to determine the frequency limit for the fiber and the film probes. The square wave test determines the frequency limits for wire probes. The time taken by the anemometer to rebalance itself is a measure of its frequency response, right? That means how much time it takes to adjust to the frequency. So what kind of a time that it takes, there is a time delay always. So shorter is the time, better is your frequency response. So the square wave test is primarily used for checking the dynamic stability at high velocities, because you want to check whether the anemometer is responding properly or not. The indirect methods cannot simulate the effect of thermal boundary layers, for example, around the sensor, which reduces the frequency response. So it's a very sensitive method. It's a very sensitive thing to begin with, and therefore it is not very easy. So there are a lot of disturbing effects. The anemometer, as I said, the problem sources. So anemometer makes use of the heat transfer from the probe. Now, anything that changes this heat transfer other than the flow variable is a problem source. Okay, anything that, so there could be unsystematic effects, like there could be air bubbles, there could be, probe can actually vibrate. It can also have contamination, which may actually increase the frequency or decrease the frequency response. There can be systemic effects, like the ambient temperature can change, it can be close to a wall, and there could be eddy shedding. So it can momentarily come and disturb this velocity, because you are dealing with a U, and this velocity may be fast enough that the anemometer will not be able to capture it. So there are multitude of what we call this disturbing influences that are already there in these kind of anemometers. So the systemic effects, that is the ambient temperature changes, the solid wall proximity, eddy shedding, bubbles, contamination, lots of things can actually can be problem sources, because you want the heat transfer to be only determined by the flow variable and nothing else. Okay, so this is a sample data. This is again taken from Professor Setajan's work. So this, and Professor Setajan and Professor Shetoprabha Choudhury's work. So this shows that how a hot film anemometer is used for measuring turbulent intensity and average velocity in a turbulent flow over a disc-shaped bluff body. So note the nature of the velocity profile. So this is the velocity profiles that it actually measures. So you can see that it measures all kinds of velocities, the mean and the turbulence. So this is effectively measured by using this bluff body stabilized flow, flame, whatever you call it. This is the flow, okay, where it shows that how the flow actually varies with respect to the sample data. So this is just a simple setup which shows that what is there in this kind of anemometers.
Now let us look into the inaccuracies that we commonly encounter in hot wire anemometer measurements. The reason why we get these inaccuracies is because the hot wire anemometer relies on the convective cooling of the probe to estimate the velocity. And this convective cooling rate can be altered by factors other than the velocity field itself. We will look into a few commonly observed scenarios to understand how this happens. And typically these inaccuracies or errors are of two kinds. They can be of systematic errors or they can be random errors. Systematic errors are consistent, repeatable inaccuracies, and they occur due to biasness in our measurement system. Whereas random errors are unpredictable variations in the measurements due to random fluctuations. We will look into again a few examples to understand the difference between the two. In systematic errors, the most commonly observed source is due to change in the ambient environment. As we already discussed, the convective cooling of the hot wire probe is what determines the velocity. That is what is used to determine the velocity in hot wire anemometer measurements. And a change in the ambient can alter the convective heat transfer rate at the probe, and this can lead to inaccurate readings. So to understand this, let us look into a very simple example. Say we have a hot wire anemometer probe that is calibrated for 20% relative humidity. So that corresponds to the black curve that we see over here. And now we are operating in an environment, say that has 80% relative humidity. And say the flow field has a velocity, true velocity of around 0.5 meter per second. So that is the true velocity of the flow field. Now, if we put this hot wire anemometer probe that is calibrated for 20% relative humidity into this environment, that would show a reading, an E value of approximately 1.4. That corresponds to this green curve, because that curve corresponds to 80% relative humidity. But since our probe is actually calibrated for 20% relative humidity, it would show that the velocity that it measured is approximately around 0.55 meter per second, which corresponds to this black curve for the same E value. So what has effectively happened is that because there was a change in the relative humidity of the ambient, we have now overestimated our velocity measurement. Similarly, if suppose we are operating in an environment that has a relative humidity less than 20%, basically less than that calibration curve, now we would be underestimating the velocity. So this is a systematic error that we have introduced due to change in our experiment, due to change in our change in the environment of our experimental setup. Another commonly encountered source of systematic error is due to the proximity with the solid wall. To understand this again, let us use a very simple example. Say we have a flat plate in our flow domain and we want to measure the velocity in the velocity boundary layer that is developed over the plate. And we are going to use a hot wire anemometer to measure it. And say suppose the plate that we have, it's a heated plate. The temperature of the plate is much higher when compared to the free stream flow. So what happens is that there will be a thermal boundary layer that will be developed over the plate similar to the velocity boundary layer. Here the temperature transitions from the wall temperature to the free stream temperature as we move along this y-axis. So this is the thermal boundary layer that we have shown here. So now if we place our hot wire anemometer probe inside this thermal boundary layer to measure the velocity, so what ends up happening is uh, the the temperature of the local flow that interacts with the probe has essentially changed. So now we are back to the same situation as we saw in the previous slide, where the parameters such as the thermal conductivity, the viscosity, the density of the ambient air, that ambient fluid that is encountering the probe has changed. So now we are operating on a different curve when in comparison to the calibration curve. So this again leads us to either overestimate or underestimate the velocity measurements, depending upon whether the plate was actually heated or whether it was a cold plate, or scenarios like this. So again, this is a systematic error because the trends are either to overestimate or underestimate. They are not random in nature. Flow disturbance due to the hot wire anemometer probe itself is an additional source of systematic errors. So a hot wire anemometer probe is basically a bluff body that we introduce into the flow field. And when we introduce a bluff body into the flow field, it basically distorts and changes the flow field around it. For example, say this is our hot wire anemometer probe that we have inserted into the flow field. And if the flow velocity is such that it exceeds a specific Reynolds number with respect to this probe geometry, it starts shedding vortices downstream of this bluff body. And this vortex shedding trail can effectively alter the velocity even upstream of this probe. So basically the effective velocity that the probe encounters is different in comparison to the true velocity. So again, this is a systematic error that we have introduced into the system due to the geometry and due to the size of our probe itself. Additionally, The hot wire anemometer probe that is inserted into a flow field can itself start to oscillate or vibrate in response to the pressure forces and the shear forces it experiences due to the flow field around it. And usually these oscillations and vibrations have a peak frequency, and therefore the flow distortions that are accompanied due to these probe vibrations are also consistent or are systematic in nature, and therefore the errors that is usually encountered due to probe vibrations are also systematic in nature. Now let us look into the most common sources of random errors. Contamination is the most common source. So the probe can basically have contaminations due to dust, oil particles, or any other particulate matter. And this depositions basically they change the heat transfer rate at the probe locally, and therefore the measurements that we get will also be inaccurate. And since these depositions are random in nature, the error that it introduces is also random in nature. The other most common source is due to electrical noise. Since we generally use an amplifier unit or a signal conditioning unit to extract out data from the hot wire anemometer probe, the components of these circuitries can be affected by electromagnetic interference, and they can introduce an additional random noise into our measurement data. Now let us look into the pros and cons of hot wire anemometer systems, especially in comparison with laser-based systems such as particle image velocimetry, which is also used to measure the velocity field. If we look into the pros, first, they are very cost effective in comparison with PIV systems, because PIV systems require us to have a laser system, a high-speed camera systems, which are relatively expensive. Whereas here, all we need is a probe, a signal conditioning unit, and a data acquisition unit, which is relatively inexpensive. The other important advantage that we have over here is that we have very high frequency response. In a PIV system, usually the maximum frequency at which we can operate is usually limited by the frame rate of the camera or the frequency of the laser system. Whereas here we are limited by the sampling rate of our data acquisition unit. The data that we get from a hot wire anemometer is usually analog in nature, and the frequency response that we get is only limited by the sampling rate of the data acquisition unit, which is again usually of the order of megahertz. So we get very high temporal resolution, and spatial resolution can also be very high. This depends upon the diameter of the probe, and today hot wire anemometer probes which are as thin as 10 nanometers are available, so we can get very high spatial resolution as well. Additionally, the accuracy of hot wire anemometer measurements are very high. The error can be as low as 1%. And the signal to noise ratio of 10 power 4 or greater are very typical of hot wire anemometer measurements. And most importantly, they are very simple to operate in comparison with PIV systems. We don't require any seeding particles. We don't require any control unit between the laser systems and the cameras that are usually done for PIV measurements. And also they are very compact and they are portable in nature. Now if we go into the cons of the hot wire anemometer measurements, they require calibration, and we are forced to operate within this calibration limits. As we already saw, going beyond this calibration limit will lead us to inaccurate readings. And also this is a point measurement technique, unlike PIV, which is a field measurement technique. So we only get velocity at a particular point in the flow field, and if we want the velocity in an entire plane, we need to traverse this probe across that entire plane, and that is quite tedious in nature. Also, this technique, hot wire anemometer technique, is intrusive in nature, basically, and that can introduce additional systematic errors that we saw previously. Also, the sensor that is used in hot wire anemometers are very fragile, and it requires very careful handling. So overall, hot wire anemometer has both pros and cons in comparison with PIVs, and they're used in different settings usually. So with that, we have come to an end of the course. Thank you.